Hello and welcome back. Today we officially start learning this course together. And the first topic we learn is Chapter 1, Interest Rates. Here I prepared some lecture slides. These lecture slides are mainly based on Chapter 1 of the required textbook written by Ruckman and Francis. So here is the outline of the first topic. In short, the essential topic of this chapter is time value of money. So the most important thing we learn in this chapter is time value of money. Okay, let's begin with the first subtopic called interest. There are several definitions here. In the first, in the box, I copied two definitions, one from Wikipedia, the other one from Investopedia. Here, this color green shows it has web link. So if you are reading the slides, you can click on these two words to go to the specific web page for more information. So let's take a look at these definitions together. Interest in finance and economics is payment from a borrower to a lender of an amount above repayment of the principal sum at a particular rate. So here, I put the keyword, underlined. I put above. So above means, let's say you borrow $1,000 from a bank. At the time of the payment, typically you will pay more than $1,000, right? So the extra amount is calculated using a specific rate. That rate is often called the interest rate. Okay. Here from Investopedia, the definition goes as follows. The interest rate is the amount a lender charges for the use of assets expressed as a percentage of the principal. So here the definition is more on the side of the value of the assets. Here, when one borrows money from another, there is a transfer, of the assets, right? So the lender transfers the assets to the borrower, and to motivate the lender for such a transfer, the borrower needs to compensate for her sacrifice. So here we have a quick notation. We use AV to denote the accumulated value at certain time t. Here, a quick interpretation is you can simply think AV as the account value at some future time. So let's say it's always suggested to draw a timeline. So let's say at 0, I borrow some money. So here's AV0, assuming I borrow $100. So the accumulated value at 0, I mean, technically speaking, it hasn't accumulated yet because it's sitting at time 0, is 100. So maybe in 1 year, this loan goes to 105, right? So in year 2, it may go to 110. So basically, AVT checks the value of a specific, let's say, account, a specific loan, or a specific mortgage, etc. So the subscript is the, you can think that as time, okay? So subscript is time, and AVT is nothing but the value at the given time, okay? The first important definition is about how we define interest rate, and here we can probably do the same thing using a timeline. So let's say here we have the account value at time t. Time goes forward by s amount of time. So right now we are at t plus s. Okay, the account value will change. Okay, so the amount of change is obviously the difference sitting here, right? The numerator part, and we use the difference divide by the starting point. So here we start at time t. So we divide by AV at t, and this is the interest rate in effect from t to t plus s. Here I put the definition of I, or the interest rate, with respect to 2 time points, the starting point and the end point. Okay, in most of this course, we don't need to be this precise. Usually people simply call I, okay? And the default time interval is for 1 year. So that means S is 1 year, okay? The default option. So 1 year. So that's the typical case. Most of the time, you will not see such a notation with the starting point and end point, but this, of course, is more precise, shows where we start and where we end while we calculate the interest rate. So here are several, important remarks. As the first one, somehow I already mentioned, that is interest should always be specified for a period of time, right? So here it goes from t to t plus s. Second, interest is the extra earned on the principal. That is why in this definition, we take the difference, right? The difference is the extra. So always keep in mind that when we talk about interest, it is the extra amount on top of the principal. The next paragraph is somehow more common. Okay, so let's consider a 1 year loan with principal AV0 that needs to be repaid at time 1. Okay, so all the payments are made at time 1, that is so-called lump sum payment. AV1 minus AV0 is obviously the gain to the lender for lending a certain amount. Here is AV0 to the borrower, right? So again, that's because usually we want to work out the interest rate for a given period, and that is usually 1 year. So this may be more familiar to many of you. Continuing the above scenario, we can define the annual interest rate, annual. So it's defined as the difference growing from time 0 to time 1 and divided by the starting point at time 0. So the definition in the previous slide is more general than this one, but this one is more hopeful to us. Finally, in the default setting, I is the interest rate per year, or is the annual interest rate per annum, and sometimes I may also use P.A. Which stands for per annum. Okay. Here I ask you to read some examples on the third page. There are a few. I think there's one example on page 3. That's very straightforward, right? So that says Bob invests $3,200 in a saving account on January 1st, 2004. On December 31st, 2004, the account balance has grown to $3,294.08. Okay, the starting value is 3,200. Okay, and it's from January 1st, 2004 to the end of that year. And of course, we can calculate the interest right? The interest is the difference. So interest is simply $294.08. And if you want to convert this into interest rate, it will be the difference, which is $94.08, divided by the initial amount, which is $3,200. So you will get an interest rate, which is roughly 2.94%. Throughout this course, I usually round the decimals to 2 decimal places. So that's why here you see 2.94. Okay, that would be the default setting. So that is the first subject. It's very straightforward, right? Next, we introduce the first way of calculating interest, how interest is grown over time. It is called simple interest. And as the name suggests, it's likely the simplest way of accumulating interest, at least from the mathematical point of view. So what is simple interest? So let's take a look at its definition. Let's say X dollars is invested in an account that pays simple interest at a rate of I per year or per annum. Then the accumulated value of this investment after T years is given by this formula. So simple interest refers to a mathematical formula of calculating accumulated value. So as long as you are given the information of simple interest along with an interest rate, you should be able to compute the accumulated value at any future time. And that's calculated according to this formula. So this is very simple. It's simply a linear function, right, with respect to time. So AV is a function of t. So left-hand side is a function of t. Of course, it also depends on the size of the account at the beginning, that is x, and also depends on the interest rate I. But usually, those two are fixed at the beginning, right? You know how many dollars you have invested. You know the interest rate you will be getting in the future. So since x and I are often fixed, so that's why I call AVT is a function of t. That's why you can see the time argument in the subscript. Note that this t does not need to be an integer. So it does not have to be accumulated value in 2 years. It can be accumulated value in 1 year and 2 months, right? So we can quickly convert the months into years, or we can even convert days into years, right? So here, let's say I want to know the accumulated value in 5 months. Then all I need to do is to use to divide by 12, because there are 12 months, in a year. And if the information is given in days, you should also convert the corresponding days into years. Typically, you will need more information because there are different counting rule, which we will talk about in a few slides. So the next one is very important. In the case of simple interest, earned interest does not accumulate future interest. That is the most important feature of simple interest. In short, if the investment is growing at simple interest, only the principal will accumulate interest. Interest itself will not lead to future interest. Okay, so that's why the growing speed is linear. So if we draw this graph, so here is AV, here is T. At time 0 is X, right? And because this is a linear function, so it goes this way, right? So at any given time, the interest is fixed. So what I mean is, so let's take x to be 1, okay? Then I have my AV1 is 1 plus I. That means the difference, okay, over 1 year. So the interest earned in the first year is I. Okay, now let's take a look at AV2. AV2 is 1 plus 2I. So if we subtract AV2 from AV1, then we see the interest earned in the second year. Okay, so here 1 denotes the first year, here 2 denotes the second year. It is also I, so etc. So in any fixed time of 1 year, it doesn't matter the starting point, the end point, as long as the length of time is 1 year, I know exactly the interest to be earned is I. So that's why, I is exactly accumulated because of the $1 investment, right? That's the meaning of interest rate, right? Interest rate, it gives you a percentage for a unit investment. So here I already set X to be 1. So the investment is in 1 unit. For any 1 year, the interest is I. And this is exactly reflected in the simple interest. That's why here, the only thing that will earn interest is the principal. Okay. We have some examples from the textbook. If you want to, so I actually recommend you to take a look at those examples. They are not difficult. For instance, we can take a look at example 1.1. Let's read the question together. Example 1.1 says, a bank account pays 3.6% simple interest. So I is 3.6%. Anna deposits 10,000. So X is $10,000 on January 1st, 2004, and leaves her funds to earn interest. Okay, the question asks you to calculate the accumulated value of Anna's account on April 1st, 2006 and January 1st, 2007. Okay, so we already have the formula. So let me write down the formula. It's X times 1 plus TI. So we know I, we know X. We just need to figure out the corresponding time T for those two dates. So T is the time difference. So for the first one, what you can do is, well, the starting point is the first day of 2004, right? It can easily go to, for 2 years, to the first day of 2006. So we know there are 2 years. And the exact time point is the first day of April, which means you still need to give another 3 months. Right? Now let's convert this in the unit of years. So it's 2.25, right? So it's 2 years and 3 months. So the first one we calculate is 10,000 times 1 plus 2.25 times 3.6%. Right? By the way, you should have a calculator for every class in this course. So if you have calculator, punch in all the numbers, it should lead to $10,000, 810. Okay, the next one is it's actually a lot easier because you can immediately see the time span is 3 years. Okay, and you can apply the same formula. The next one is 1.2. Example 1.2. This is example 1.1. Here, a bank account pays 6%. Simple interest, Randy deposits $100 and leaves his funds to earn interest for 2 years. So which means T equals 2. Okay. We can quickly calculate for Randy. So at the end of 2 years, Randy will earn this amount according to simple interest rate. So what I have is $112. There's another guy, Leonard. Leonard withdraws his accumulated value at the end of 1 year. At the end of 1 year. Okay, so Leonard. So he withdraws his money at the end of 1 year, I mean, for the same $100. So invested for 1 year. So it's obvious the amount is $106. Unlike Randy, Randy holds the deposit for 2 years. So here Leonard makes 100 deposit at time 0 and takes out $106 by the end of 1 year. And then he immediately deposit 106 again into the same account, earning the same interest rate. At the end of year 2, we have 1 times 1.6. By the way, here there's a little misuse of notation because usually when we use ABT, the meaning is x is at time 0, right? And here is AVT. So, but obviously this meaning is slightly different, right? This means the account value at the end of 2 years, okay? But I calculate this amount for just 1 year because, or Leonard just does the calculation for 1 year because he actually withdraws at the end of 1 year and do another deposit, right? So technically speaking, this is also AV1 in the case of Leonard, but here for the comparison purpose and also to make sure this T denotes the actual time. So we have somehow followed a little misuse of the standard notation. But anyway, the most important thing is here. So this amount is actually bigger than what Randy will get at the end of 2 years, right? So this is, well, technically speaking, in mathematical terms, we often call this contradiction because at the beginning, both Randy and Leonard have $100. But at the end of 2 years, Randy has $112, but Leonard has 36 cents more. So it's somehow a contradiction or paradox, which we will talk about in the future slides. Okay, just keep in mind that how one invests is important, in particular if the interest is in simple interest, right? So here Leonard is the smarter one, among the two. He actually knows more of financial mathematics, so he takes the advantage of withdrawing and depositing again. Okay. Here is the one I mentioned earlier. Sometimes between 2 dates, when you do the counting, you get number of days, and you need a certain rule to convert the number of days into years, because in practice, all the interest rates are quoted with respect to 1 year. Okay, so we will need to do the conversion, and this is often referred to as day count convention. Okay, somehow this is not mentioned in the textbook, so I'm not sure whether SOA will test this. But anyway, it is very, very important in practice. Here I list several common counting rules. The first one is called 30 over 360. The meaning is 30 means there are 30 days in each month, and the 360 means they are 360 days in 1 year. So with this rule, I don't care whether that month is a February or not. Right? As long as it's a month, I use 30 days. Okay, and also I don't care whether a particular year is a leap year or not. As long as I know this is 1 year, I assign it with 360 days. So the rules says that 1 month equals 30 days. 1 year equals 360 days, regardless of whether that month actually has 30 days or not. Okay, so with this rule, we have this conversion formula, which is very obvious. The rule is reflected here. You use 30 days times the difference in months, and you use 360 days to multiply by the difference in years of 2 dates, obviously. The next rule is 3365, and the meaning is obvious, right? So now we take 1 year to be equal to 365 days instead of 360. So that is the difference. The third one is called actual over 360. So when we calculate the days, well, we do not use any rule. We actually count the days between 2 days. So that's why the numerator is now actual. It's the actual number of days between 2 days. Of course, there are more rules, like in the first one is actual over 365. So the difference is how we count 1 year, and it can also be actual, although this is not common. Again, the meaning is straightforward, right? So this actual means the number of days between 2 days. This actual means the number of days in a particular year. Okay. So here we have an example. So in this example, we have simple interest rate to be 5%. You deposit $100 on September the 4th, 2020, a few days from today, and withdraw the entire amount on December the 8th, 2020. What would you get upon withdrawal? So, of course, here the first thing you need to do is to, depending on the rule, right? So if you want to know the actual days, I actually give this number to you. If not, you actually need to count. You need to get a calendar and count how many days they are between these 2 dates. Many software like R, like MATLAB, have built-in functions to get you the actual days between any given dates. Okay, no matter how crazy in future or how crazy in the past those 2 dates are. Okay, the software can quickly get the answer. So now let's take a look at how this affects the computation, okay? So first, let's look at the actual over 365. So now I have actual 95 days between 2 dates, and I apply 365 to 1 year, okay? So now this is my time, T. I convert 95 days into the unit of year, okay? And I get this number. It's slightly, of course, it's a little over 3 months. So the interest rate is not crazy. It's a little over $1. Next, I do actual over 360. So it's the actual number of days divided by 360. I get another number. Obviously, this is greater because there are fewer days in 1 year, and then that means when I do the conversion, time t is slightly bigger, right? So this t, so let's call it T1, T2, and call this T3. So obviously my T2 is bigger than P1, right? So my AV in the second rule is bigger than my AV in the first rule. Finally, let's take a look at something different. So here we apply 30 over 360. So the first thing I'm going to do is to calculate how many days under this rule, right? The actual number of days is 95. Okay, now let's see how many days. So let's first do the day difference. So it's 8 minus 4. So there are 4 days difference. Okay, next let's do the difference over months. Here I apply 30 days for each month. And here I know the month difference is 3, like 3 months. So together I have 90 days. So if I apply this rule, the number of days I get is 94 instead of 95. So that's why the day count conversion very matters. And the different financial products actually apply different rules. So it is very important for practitioners to know which rule their product apply. Otherwise, it could lead to disastrous results. Okay, so here, the difference is just 1 day, and you can see the amount is probably not that different. I mean, here if you apply 95, you get slightly different amount. Here, slightly more, but keep in mind that in the money market, so in bonds, in treasury bills, financial institutions, they buy in million, sometimes even $billion. So a tiny decimal difference could lead to a huge thing. So that's why knowing the difference or knowing the rules of a product is very important. I guess I will stop here for this video. In the next video, I will talk about something which is irrelevant to this course. That's because those topics are very advanced, but I believe they are truly interesting. So if you're interested, please take a look at the next few slides, okay? And we will go over them in the next video.